Okay, so now that we've decided what the slope represents and what the y-intercept represents, let's kind of like take it one step farther. So this equation that we have here, x is equal to negative 52 centimeters for each second multiplied by time plus 1 centimeters, is just like a hypothetical example of an equation that you would have found in one of your trials, let's say one of the third trials. And remember, x represents position, t represents time. And somebody tell me, what did we say the y-intercept represented about this object?
The starting position.
Starting position, good. And somebody else remind us what we said the slope tells us about the motion of the car. And
The speed.
yes, it tells us the speed. Now, this number and these units, 52 centimeters each second, that tells us how fast it's moving, right? But the slope has actually one more piece of information in it that's more than just the speed. What does that negative sign, Deanna, tell us? Dan?
Direction.
Yeah, it tells us direction. So the slope tells us both speed and direction. So the slope is not just speed, it's more than that, because it can tell us whether it's moving forward if it has a positive steepness, or backwards if it has a negative steepness. And in physics, we call that velocity. So the slope is not just speed, it's velocity, and velocity is how fast something is moving and what direction it's moving in. So this equation right here relates to, let's say, a toy car that's moving at 52 centimeters per second in the negative direction that started at a position of 100 centimeters. That equation only has predictive capability and power for a toy car. But remember, we want to do this experiment to learn something about any object or anything that moves at a constant speed, not just toy cars. So let's replace the slope and replace the y-intercept with what it actually represents. Okay, so I'm going to rewrite this equation. This is going to be our general equation. And this does not have to show up in your formal lab report. Okay? So we have position, or x, is equal to the velocity of an object. I'm going to use a capital V, multiplied by time, plus our starting position or initial position. And we just use an x sub 0. And that means your starting position or the position of the object at time 0. So now this a general equation applies to toy cars, it applies to planes, it applies to sound or light or any other thing that moves at a constant speed. We can predict the position of something if we know where it started, our initial position, how fast it's going and in what direction, its velocity, and how long it's moving for. So how much time is it moving at that velocity? Okay? And so now we can predict, how far light would travel if we know what its velocity is, 300 million meters per second, and how many seconds it's moving for. We can predict exactly how far that light will actually travel, okay, and be accurate. Because we know, there's ways we can figure out the fact that light does travel at constant speed and decide or measure what that velocity is. So in your lab report, basically you guys can now write your conclusion in its entirety. And this term velocity is a new term, which means you need to now do number 6 and number 7 in the conclusion. Number 6 is define any new terms. So you guys just have to define what velocity is. And number 7 is, how does that new term relate to the lab, or where did it come from? So how would you answer that question? How does velocity relate to the lab that you guys just did? Anybody? Yeah.
Velocity would be how fast the car was going and in what direction.
Yeah. So velocity would be how fast the car is going and in what direction, and where did that come from on our graph or in our equation? Yeah, it came from our slope. So the velocity was the slope of a graph. We have to be a little more specific than that. We have to say that velocity is the slope of a position versus time graph. You can't just define the slope of any graph and that's the velocity. It's only the slope of a position versus time graph.